am V. Tramal Rao, pursuing secondary BTech in ECE branch with roll number 24BQ1804I6. Today my topic is about stationary process. Stationary process is said to be stationary if all its statistical properties such as mean, movement, variances, etc. do not change with time. This means the probabilistic behavior of the process remains the same even if we shift the time axis. The stationary of a process can be classified into different levels or orders depending on how the probability density function behave with respect of time. First order stationary process. Random process is said to be stationary order on if its stationary first order probability density function does not change with time or with any shift in time. If x of t is first order stationary process, then fx of x1 fx of xi t1 equal to fx of xi t1 plus delta t for any time t1 where delta t is a shift in time. This means the probabilistic density fx of xi t1 is independent of the actual time instant t1. Therefore, the mean value of the process remains constant with time. Hence, for a first order stationary random process, the mean value must remain constant at all time instants. E of x of t equal to x bar equal to constant. Proof. Consider a random process x of t with random variables x1 equal to x of t1 and x2 equal to x of t2 at time instants and t2 equal to t1 plus t delta t respectively. The mean values are e of x1 equal to e of x of t1 equal to integral minus infinity to infinity x1 fx of x1 t1 dx1. E of x2 equal to e of x of t2 equal to minus infinity to plus infinity x1 of x1 t2 dx1. Now substitute t2 equal to t1 plus delta t. Now e of x of t1 plus delta t equal to integral minus infinity to infinity x1 fx of x1 t1 plus delta t dx1. For a stationary process, we know fx of x1 t1 plus delta t equal to fx of x1 t1. Therefore, e of x of t1 plus delta t equal to integral minus infinity to infinity x1 fx of x1 t1 dx1. X of e of x of t1 plus delta t equal to e of x of t1 equal to a equal to constants. Hence proved that for a first order stationary random process, that means the mean remains constant with time. Now second order stationary process. A random process is said to be stationary to order 2 or second order stationary if its second order joint probability density function does not change with time or with any shift in time. In simple terms, if we shift the time axis, the joint density function of a random variable set to time instants and remains the same. Mathematically, fx of x1 x2 t1 t2 equal to fx of x1 x2 t1 plus delta t of comma t2 plus delta t. For all t1, t2 and delta t, this means the function depends only on the time difference t2 minus t1 and not on the actual time instants t1 or t2. Note that every second order stationary process is also first order stationary process because if the joint distribution does not change with time, then the individual distribution also remains unchanged. Condition of second order density function process stationary. For a process B second order stationary, its autocorrelation function should depend only on the time difference between two instants and not on the absolute time. Let x1 and x2 be the random variables of a random process x of t. At time instants t1 and t2 respectively, the autocorrelation function is given by rxx of t1 comma t2 equal to e of x of t1 and x of t2. If we define tau equal to t2 minus t1, then rxs of t1 comma t1 plus tau equal to e of x of t1 e of x of t1 plus tau equal to rxs of tau. This means RHS of tau depends only on the time difference tau and is independent of the actual time t. White-sense stationary process. If a random process x of t is second order stationary, it is called White-sense stationary process of a weak-sense stationary process. However, the reverse is not necessarily true. A White-sense stationary process may not always be fully second order stationary. The condition for a process to be White-sense stationary are the mean of the process is constant with time, v of x of t equal to x bar equal to constant. The autocorrelation function depends only on the time difference tau and not on the absolute time t. V of x of t plus tau equal to RHS of t. Thus, for a White-sense stationary process, both the mean and the autocorrelation remain the same regardless of time shifts. Joint White-sense stationary process. Consider two random process x of t and y of t. If they are joint White-sense stationary, their cross-correlation function depends only on the time difference between the two time instants and not on the absolute time. The cross-correlation function between x of t and y of t is defined as Rxy t1, t2 equal to e of x of t1, y of t2. If we let tau equal to t2 minus t1 and t2 equal to t1 plus tau, then Rxy t1, t1 plus tau equal to e of x of t1, y of t1 plus tau equal to Rxy of t. This means the Rxy of tau depends only on the difference tau. The condition for all two processes to be jointly White-sense stationary are v of x of t equal to x bar equal to constant, v of y of t, y bar equal to constants, e of x of t, y of t plus tau equal to Rxy of tau, which is independent of the absolute time. Now, strict-sense stationary process. A random process x of t is said to be strict-sense stationary process if it is nth order joint density function does not change with time or shift in time value. Explanation is the statistical properties of x of t at n time points remain the same regardless of when observed or shifted by delta t. For example, x of t1 and x of t2 behave like same x of t1 plus delta t and x of t2 plus delta t. Same as equation of strict-sense stationary process is fx of t1 and so on x of tn of x1 so on xn t1 so on to n equal to fx of t1 plus delta t so on x of t1 plus delta t of x1 of so on of xn t1 plus delta t of so on t1 tn plus delta t. A process that is stationary to all orders n equal to 1, 2 and so on n is called a strict-sense stationary process. In explanation, this occurs when the process maintains time invariance for all orders, meaning all statistical movements are constant over time. And now, a strict-sense stationary process is also a White-sense stationary process, but the converse is not true. Explanation: a strict-sense stationary process invariant for all n, including White-sense stationary, where mean and autocorrelation are time invariant, but a White-sense stationary process may not be strict-sense stationary process if higher order statistics vary. If stationary conditions hold for n less than or equal to k, but not all n, the process is stationary to order k. Explanation of this is the process is time invariant only up to order k, with higher order dependencies potentially changing with time shift. Coming to the session, we know about stationary process. In the stationary process, we know definition of stationary process and first order stationary process and their mathematical equation and their proof. And now secondly, first order function that remains constant with time equal to and second order stationary process. In this second order stationary process, the mathematical equation is fx of x1 x2 t1 t2 equal to fx of x1 x2 t1 plus delta t t2 plus delta t. And condition of second order process. We know about condition of second order process. This means Rxs of t that depends on time difference and independence of the actual time. And after we know about weights and stationary process, the process with time and difference with time, and we know about jointly right sense stationary process. After that process, in this process, cross correlation between x of t and y of t, and about stationary function process. Thank you.